All right, so a few reminders and announcements. Standard reminder, Muddy's Point this weekend. Then there is the next chapter in the Mitchell text, chapter 3 on information is for Tuesday. The reading is available. I'm almost done with the reading exercise. I did finish assignments C and D and release them. So these are those unit comprehension assessments that you get drop 6, and I think there are going to be like 11 total. I released them together and I gave them a common due date of Wednesday, which means they'll actually be available until Thursday night because I give that 24-hour grace period. If you want to attempt them, then have them count towards, again, there's drop 6 on those. Feel free to do so. Again, C is over resilience thinking, D is over basically chaos and complexity. Then there is not a unit comprehension assessment for E because E butts up against the midterm. So I have a midterm review assessment that is ready but will not be released until after Wednesday, because this midterm review assessment is going to just randomly sample questions from the previous assessments, plus a few questions that I added for Unit E. So Unit E is sort of folded into this one. You'll be able to take this as many times as you want. Your highest score will be kept, it's 45 points instead of the standard 35. So that's not bonus points, but it'll mean that if you were to score 100% on this one, it'll buffer any points lost a bit. So because it's worth a little bit more. So because you can complete it an unlimited number of times and it's extra points, then it's an opportunity to buffer. So I would say that whereas you might be considering that, well, maybe I don't want to do both of these assignments, I would recommend doing this midterm review assignment. For one, it's good studying for the midterm that's upcoming. 2 is if you have a good opportunity to do well and then buffer your score. So I think that's pretty much it. So just a reminder on the timeline, we're finishing Unit D today. Then we talk about information, the physical basis of information next week. That'll be Unit E, Tuesday and Thursday. And then the week after that, Tuesday will be a midterm review period. So we'll come here. I can try to come up with sort of greatest hits just to get ideas going, but that's primarily there for if you have questions, if you need to work some problems or things like that, then that's sort of there for us to review that together. But again, I can try to provide some sort of seeder content, like what do I think are the greatest hits from the 5 units. And then that Thursday after that will be stage 1 of the midterm. And the way the stage 1 works is you'll have all of Thursday, and I'll think I'll probably release it maybe Wednesday, Thursday, and Friday, or Thursday, Friday, and Saturday. I'm sort of waffling on which one of those, but I'll sort of figure out which one of those options. But I'll give you multiple days to do it. You can come to class with your laptops and do it in class, but it'll be a 90-minute window I'll give you just for any technical difficulties. And this class is a class right after it. So if you come to class, you'll have to end in 75 minutes. But if you want to take it at home or somewhere else, you'll use Respondus lockdown browser for stage 1. So you don't have to come to class for that one. There'll be no attendance that day. So it'll be your freedom. So if I release it on Wednesday, then you could do it anytime Wednesday, Thursday, or Friday. But once you start it, you'll have 90 minutes to complete it. Then you'll have over the weekend, you won't see your scores, you won't see the right answers, but you'll know what the exam was. And so you'll get scrap paper that you can use on that, a couple of sheets of blank paper you can bring with it, on as well as your 2 double-sided formula sheets. And you could write down sort of what you thought were the hardest questions and all that. And then on the Tuesday of the week after that, we'll do stage 2. And stage 2 will just be available. And again, I think I'll make it available maybe Monday, Tuesday, and Wednesday. I haven't decided on the exact days, but I'll give you a couple of days. And during that period, you can work with your partners or work with other people in the class. You can use the Canvas. You can use any of the textbooks. Anything I've provided, you can use. And then anyone currently enrolled in the class, you can collaborate with, and to do that stage 2. And then your stage 2 will be 20% of your total midterm score. Your stage 1 will be 80% of your midterm score. And then once stage 2's availability window ends, then I'll release the correct answers and the scores, and we'll just roll on with Unit F after the midterm. So that's how things are laid out. Any questions about timelines or assignments? Yes. It's on the Canvas calendar, but so if we count ahead, next week is Unit E. The week after next week, that will be the stage 1. So it's, I think, don't quote me on this, but I think it's February 23rd is stage 1. So it will be 2 weeks from today. And again, so 2 weeks from Tuesday, the previous Tuesday, will be a midterm review where we'll just sort of have an opportunity to sort of go over units A through E, any questions, any clarifications. And that's a big reason why the midterm review assignment is due before that lecture, which is, well, it's due February 20th, but you'll be able to turn it in February 21st because I got that 24-hour grace period. But the intent is that you can do the review assignment and say, oh, well, now that I've gone back and done those questions again, I realize that maybe I don't quite remember what the difference between resilience and adaptability is. Can we go over that? That sort of thing. All right, any other questions? Okay, good. All right, so wanted to make sure that we kind of got, this chapter that you read was primarily, I wanted you to see Mitchell's definition of complexity and complex systems and complex adaptive systems. So she, like many others, drops the adaptive and just assumes that all complex systems of interest are complex adaptive systems. So we'll get to that, and I'm interested to hear your thoughts about it. But I want to make sure, because chaos came up as an important topic, and that's really what this unit is about. And we kind of went a little more rapidly. I want to make sure that we see where chaos comes from. So let's just take a quick digression there. And remember that where we ended before is that we basically said, we were talking about systems with delays. And I kind of was talking about how when you have systems with delays, then the ball and basin model sort of fails to be that helpful, because it's almost like if you had one of these basins and you had a ball rolling around this basin, it's almost as if the forces acting on the ball come from a position in the ball's history. It's like some weird, time bending movie where where you're living now, but your sensory experience is a day ago. It's so, as a consequence, then instead of getting a ball that settles down at what you'd expect to be the equilibrium, you get this ball that is just oscillating back and forth on this hill. So oscillations often occur here. So and we've heard about this when we talked about systems archetypes. And so we said, if there's balancing with delay, so if we consider balancing feedback, the simplest balancing feedback with delay would be some sort of measurement of a gap. So if I want to map it directly to my little ball and basin model here, I could call this point A, call this point B, call this point C. And, I could say, well, if I have my gap, I'll say gap above B or gap to the right of B. So if you're at A, it's positive. If you're at C, it's negative. Well, if that produces, if the gap above B produces a movement to the left, but that movement is significantly delayed. And then that movement to the left, eventually when it happens, it will reduce the gap above B in principle. So if you manage to move to the left, you'll get closer to B. But if you have this delay here, then what you can end up having here is that when you get to B, the action that should shut off keeps acting. And so movement that started out moving toward B will just keep moving towards C. And it may not be until C that that movement, that force shuts off and then starts going the other direction. And so that generates more of an oscillation than a settling down into the basin. And so that, if we plot the behavior over time of such a system, then what we can get is we still get sort of these transients. Like if we start at some initial condition, let's say this is A, this is B, and this is C. If we start out at some position, less than C, it might ramp up, but instead of hitting B, it might go all the way up to A, and then come back down and oscillate towards C, and then have these like stable oscillations. So we could get stable oscillations. So I say it's stable because it doesn't grow. Or what can happen is if the delay is not quite that bad, it's enough to slow down the kind of stabilizing force of the basin, then it's also possible to get damped oscillations. So if I draw this in a different color, maybe a little more gray. So if I start at the same point, I might get a system that looks like this. And so we refer to those as being damped oscillations. And then I could also have growing oscillations. And so an alternative is I could have, and I'm just gonna maybe scribble it. Well, I'll see if I can put it on top of this, but the other option is, it goes up, it comes down, and then it gets bigger and bigger over time. So these are growing or unstable oscillations. All right, so it's a little bit of a mess there. Hopefully you can see that the black one stays constant, the gray one kind of damps out. And sometimes in the damped case, we refer to that phenomenon as ringing. So we can say that the system rings a little bit. Just like a bell. If I whack a bell, it makes it oscillates at a tone, but that tone gradually reduces its magnitude over time because the bell ends up losing energy. So, but if the bell could ring forever, then we would just say that's a stable oscillation. All right, so any questions about these three possible phenomena you can get here? This is the complication you can get when you have delays in your systems. You can get these oscillations start to occur. Now, what I want to point out here is that so far in this class, when we've talked about attractors, we've talked about point attractors. And so we've talked about things that, like in this ringing case, that B is a point attractor or a stable equilibrium point or a stable state for the damped oscillations. So that's, that kind of matches our intuition so far. If you start in the basin of attraction of an attractor, some transients happen, but eventually, as time goes to infinity, you land at a point at the bottom of a basin or something like that. But what this shows that there's a possibility for our attractors to be dynamic, that we can have a pattern that goes on for, practically infinite amount of times. It's not a point where the system just gets locked in a cycle of going back and forth. And you can, like, for example, people talk about the pendulum of the American political system. It swings to the left, it swings to the right, it swings back to the left over time, and it just goes on. And you could argue that the reason this happens is because you have to wait for people in power to become so bad that people decide to vote them out. But that takes time, and then they get voted out, and then the other party, the alternative stable state, sort of starts driving it that way. And then that leads them to be so bad in the other direction. And then it kind of goes back and forth. And there's enough energy in the system, like a bell that rings forever, that it just oscillates. And so that's an example of the stable state there is the oscillation. You're never going to settle down to have 50% one party and 50% the other party. And so that suggests that for like the dark line, we have this A to C oscillation is a stable, and I'm going to call it set. So it's a set of points that's the attractor. So this is something called a set attractor instead of a point attractor. So it's still stable, it's not growing, but it's not a single point that the system settled down at, it's a pattern. So you get into a stable pattern, and that pattern repeats forever. So I could call this a stable pattern of behavior. And we could say repeats forever. And then this, as an example, American political system. And that's left, right, so on. Okay, any questions or thoughts about that? Does that make sense, what I'm sort of saying here so far? Is that it's possible to have these dynamical systems that oscillate, and that oscillation becomes what we refer to as a set attractor instead of a point attractor. It's a pattern that the system is attracted to instead of a point. And that often happens because you have delay. Okay, so we'd say, all right, when I had a point attractor, if I started anywhere in the basin, anywhere in the region of stability, it doesn't matter where I would start, I'd always land at the point. What happens when you have an oscillation as your stable attractor and you try different initial conditions? Well, every initial condition will lead you into a pattern that is recognizable, that's stable. But now the phase, the sort of like where the pattern starts, is going to be affected by the initial condition. So, so say here, with set attractor or with stable oscillations, initial condition sets the phase. And what I mean by that, if I were to draw it here, is that if I start, if I'm oscillating from some point to some other point, if I start in one spot, I might get something that looks like this. But if I start, let's say, right within the oscillation, it might, and there might not be any transients, it might just kind of start going. So maybe if I start here, it goes up and the frequency looks the same, the amplitude looks the same, but it's shifted. If I start way up somewhere else, there might be some interesting transients, but then once it lands here, it might be right on top of the black line. Or if I go start in a slightly different spot, then there might be some interesting transients again, but eventually it gets down here and might have yet another phase. So, there's a phase shift that is linked to the initial condition. And so what we see is that with point attractors, there was no sensitivity to initial conditions. So a point attractor, no sensitivity to initial condition, IC. But a set attractor, there is some sensitivity to initial conditions. It still basically operates the same, but it's just shifted around a little bit. So, but the point here is that this is what delay did. So delay caused this sensitivity. All right, any questions about that so far before we make things, take things chaotic? Yeah. Yeah, so we would say that that this, it's a great question, and I should make this clear here. So let's, technically the basin of attraction for this system, like, so let's call this is the stability regime. But this right here is actually the kind of stable set. So before I had an equilibrium state, now I have an equilibrium set. So I can say this here is like my stability regime. So any initial condition that starts in this this regime here, and in this example, might as well go all the way up to every single value. All of that will eventually land up into this stable set, as opposed to a stable state or point. So it's like all of these initial conditions eventually land here. But you can't be multiple points at once. So that means you're going to be moving around. And the way you move around in this case, it looks roughly the same, but where the pattern starts is going to change with where your initial condition is. And so, whereas in the point attractor, all initial conditions, like once you hit carrying capacity in that fish pond, you have no idea where you started. You lose all that. But if you somehow know something about the phase of these oscillations, you might be able to kind of work backwards to figure out gesundheit where the system started. So there's some hint of the initial condition in the shift of this oscillation. Does that make sense? Okay. All right, so that's not chaotic just yet, but it shows that delay starts to set things up to get really kind of complicated. So, so how do we go from complicated to complex? Let's say now add nonlinearity. Or nonlinear feedback. Well, what do I mean by nonlinear feedback? Well, we can write an expression, like a statistical expression that says the changes in one of our endogenous variables tends to be related to the values of our other endogenous variables. So we can say change in endogenous variable equals, and then some mathematical function here. And I'm not going to get very math, we're not going to do numbers here, but I just want to, because we see the word nonlinearity all the time. What does this define? What it means in systems thinking here. So the change in some endogenous variable, if we can turn that into a linear sum, and what I mean by that is, let's say we have a bunch of endogenous variables, I'll call them X, Y, and Z. If we can come up with some numbers like A, B, and C, and add them up together so that these here are 3 endogenous variables, and these here are just constants, they're numbers. That right there is referred to as linear, a linear combination, or this is linear, and I'll say feedback, because let's assume that one of these endogenous variables is like the change in X over time. So here we're saying that how X changes over time is related to whatever X's current value is, plus whatever Y's current value is, plus whatever Z's current value is, where X might be number of students in the class, Y might be temperature in the classroom, Z might be day of the week, or I don't know, something along those lines. And A, B, and C is like how important those things are. So if the number of people enrolled in a course depends greatly on the number of people currently enrolled in the course. Like if you see that a lot of people enrolled in the course, you're more likely to enroll in it, then A might be a very large positive number if we're trying to describe how the enrollment changes over time. But Y might be, the course number. And you'd say, well, I don't actually care much about the course number. And so, if that has very little relationship on how many people enroll in a course, then B might be very low. And so on. So you can come up with a model where you sort of say, here are all of the things that might influence this change in this variable. And here's how we weight them so that we can say one thing's more important than the other thing. And this is linear feedback. So there are questions about that. This makes sense that we can write that sort of thing. Now, if we can't write that, if there's no way, and I'll give you an example of this, a concrete example in just a second here, then it's nonlinear. So otherwise, nonlinear feedback. So it's the inability to write things that way makes it nonlinear. So let me see, let me make sure I don't jump the gun here. Yeah. So here's an example of that. This is example. This is a nonlinear feedback with delay. So this is a system called the Mackey glass system. I'm not going to ask you, you're not going to have to memorize this. I'm just putting it up here as an example of a system that looks pretty simple if you break it down, but has these weird dynamics. And it's because of this nonlinear feedback and delay. So it's called the Mackey glass system. And this was a model actually of built, it's a physiological model of, I think, how how blood is synthesized, how red blood cells, I think, are synthesized based on the current concentration of other things in the bloodstream. So you could imagine that you could have like an endogenous variable, which would be number of red blood cells, and that number of red blood cells might depend upon the current number of red blood cells. And so if you have a low number of red blood cells in your bloodstream, then maybe your body ramps up production. If you have a high number, maybe it slows it down. So, and it turns out in order to match the physiology just right, then they had to come up with this expression. And instead of writing change, an endogenous variable, they use a calculus expression for it. And this is just like you read in your book that Newton had to come up with calculus in order to really start talking about these changing systems. So they write dx dt, but again, we're not going to do any math here. We're not going to solve any equations. This is just the change in the endogenous variable x. So this is just change in x. And they say that change in x is going to be a function of the x at a value sometime in the past. So this is a delayed version of x 2 time units ago. And that gets multiplied by this fraction, and this is what's going to make it nonlinear. It has 2 in the numerator, and that doesn't matter. But then the denominator, it has 1 plus, and then this x t minus 2, and that thing's raised to a power that I'm just going to write as n. Again, all the details here are not that important. All I really want you to focus on, I'm going to make this a dot so it doesn't look like another x, is that this here is nonlinear. If that fraction was just a 2, this would be linear. It would still be delayed, but it would be linear. But because that's not a constant, because it has the value in it there too, this is nonlinear. So that's nonlinear feedback. And then it happens to have out on the side minus x at the current value. And so this right here is good old-fashioned linear feedback. So there we've got delay, and we have nonlinear feedback. Looks a little ugly, but if you really think about it, this is not that different than a fisheries model that we've already seen. This is like the net regeneration rate of fish. This over here is like the death rate, or like deaths of fish. So you can imagine every fish, x, has some probability of dying, which is the constant in front of x. And this right here is like a fish birth rate, or fish births with carrying capacity. So as the fish get larger and larger, then the birth rate changes. So if you think about the logistic math that you might have seen in SOS 101 or those sorts of classes, there's a very similar formula here. It's a different expression, but it operates in a similar way. If there's 0 fish in the fishery, then this thing's equal to 2. If there's a very large number of fish in the fishery, then this thing is much less than 2. So it acts like a carrying capacity, where the number of fish in the fishery changes the birth rate per fish. But it doesn't, in this case, this has not been built to describe fish. It's been actually built to describe the way blood is synthesized, like new blood cells are synthesized in your bloodstream. And so that's the Mackey glass system. So it looks, like I said, not that much different than a fishery, but this parameter here, n, which is a little bit like deciding how big the carrying capacity is. If depending on how big you make that n, that exponent, then you can get some really ugly behavior here that I'm going to show in just a second. So before I do that, are there any questions about this? Again, I'm not asking you to memorize this. It's just an example that when you combine delay with non-linear feedback, you can go from having nice oscillations to something that's much worse. All right, so let me copy over. So these are my instructor notes. I'm just going to go ahead and copy one of the diagrams that I've got cached there and paste it in here. Not seen. All right, so this is our kind of first example here. So when you take SOS 212, you'll be able to take an expression like this, that's our Mackey glass system from the previous page, and turn it into a stock and flow diagram like this. And once you do that, you'll be able to hit play in a program like Vinsim. And it's a really simple stock and flow diagram, one stock, two flows. And when you hit play, you can get outputs in Vinsim or Insight Maker or whatever tool you're using in your 212 class that look like this. And I'm going to zoom in on this here for a second. But what I've lined up here is that I basically ran this system with three different initial conditions, starting X at one value, another value, and another value. And then I just saw what would happen. If this was a fishery, then it would rise up and it would level off at some value regardless of where I started it. But this isn't a fishery. It's got this ugly nonlinear feedback here. And when this exponent is really high, when the exponent is low, it actually behaves a little bit like a fishery. So really low values of this exponent, this thing will level off at 1. Slightly higher values of this exponent, this thing will actually oscillate back and forth around 1. As you get larger and larger values, this thing starts getting these little extra steps in its oscillation and start looking pretty ugly, but still all of the points kind of land in roughly the same pattern. But once this exponent here reaches, I don't know, it's around 9. So once this thing goes to about 9 or higher, then this thing exhibits what is referred to as chaos. And that's extreme sensitivity to initial conditions. And so what you can start to see here is it's actually closer together at the start than it is out here. So what we can see is that our choice of initial condition leads to vastly different trajectories later in the system. It never quite stabilizes. If I zoom in farther, I'll go here. So I'll grab maybe both of these. So if I zoom in a little farther here, then what we see is that, so this is going only to time 50. So it's, you can see that the initial conditions start close together. It kind of has a similar look in the beginning, but then it starts spreading out. And actually each individual behavior isn't just shifted left and right, it looks different. And if I then zoom out so that I'm looking at, or zoom over so that I'm looking at time 400 and 450, it never gets any better. So I've gone from a nice sort of, this is still stable. This is not exploding. So this is still stable, but it's not oscillating in a recognizable pattern. It's like every pattern, every initial condition has a different pattern. All of the patterns stay roughly close together, and that's what we refer to as global stability. But locally, it's very unpredictable in how it's going to run. And in every different way it could run, it depends upon its initial conditions. But it's got extreme sensitivity to initial conditions. And that right there is chaos. And so this has sort of locally unstable, but globally stable. Yeah. Excellent question. So what is its attractor? And this is what's referred to as a strange attractor. And in the next system, we'll actually visualize this a bit better. But what a strange attractor is, so basically if I won't draw, I actually have an auxiliary reference in this unit that if you'd like to read, you can look at it. And it plots the bifurcation diagram for this system. It's actually called an orbit diagram, but it's basically the same thing as a bifurcation diagram. And what happens when you draw a bifurcation diagram to a system with chaos is you get an exogenous variable like this n. So this is an example, so bifurcation diagram. Sketch for Mackey glass system. So basically you have your exogenous variable n, so that's your exogenous. And then you've got these points that, there's sort of, we'll think about it, the points that it reaches sort of infinitely often. And for say something up to around 5, there's just one stable attractor. Around 5, then it actually starts oscillating. So I think it's up to like 7, you get oscillations of growing, and I'm just going to draw them as dashed lines because it's, I don't want to belabor this too much, but you basically get oscillations with growing amplitude. So this n value, at 5, it looks like a fishery. It rises to 1 and stays there. From like 5 to 7, it actually oscillates from one amplitude to another. And so in a bifurcation diagram, we often will just write, that there will, that we indicate the amplitude of the oscillations. And we say that from 5 to 7, those oscillations grow, but they still look like a normal oscillation. From like 7 to 9, you start getting what's referring to as period doubling, which in the chapter, if you keep reading past page 22, Melanie Mitchell talks a lot about period doubling for another system that's the logistic map. And so basically what that looks like is something along these lines where you start getting, and I'll explain what I'm drawing here in just a second, but basically every branch that I'm drawing here, this is still oscillatory behavior, but every branch that I'm drawing here represents a new point that it hangs out in around at the edge of its oscillation. So like here, it looks like a sine wave. It goes up, it comes down, it goes up, it comes down. Once you get period doubling, then what you get is it might go up and then down a little bit, and then up again, and then down a little bit, and up, and then way back down. And so every little bend is one of these lines. And so every time this forks, you get like a new bend in the oscillation. And it extends what we call the period of the oscillation. Now, the crazy thing that happens at 9 is basically the number of these forks goes to infinity. And so if you were to draw this, this bifurcation diagram, it would just become kind of like this dense mess where you wouldn't be able to see what was going on here. And this here is referred to as a, well, actually I could say this point right here is referred to as a descent into chaos. And it's hard to wrap our heads around what's going on here. In the system, what's effectively happening is you get an infinite number of unstable equilibria or thresholds. So basically what happens is that when you're in this crazy region, this Mackey glass system, that X variable, when it is constantly being pushed away like a pinball in a terrible pinball game, it's constantly being pushed away from a point into another point that gets pushed away from, and then gets pushed away from. It keeps being pushed away and eventually gets pushed back into the group. And that's what makes it globally stable. But when it's in the group, it can't find any basins of attraction to settle down in. It's constantly being pushed away. So it's just imagine, you know, we've got like a bunch of kids on a playground and there's one kid in the middle and they just keep getting pushed and they never leaves because they always get pushed back in, but they never settle down. They just keep being pushed around in this sort of group. And so that's chaos right there, is that the mathematical basis of chaos is, coarsely speaking, this is sort of a little bit of an oversimplification, but it's an infinite number of unstable equilibria, and that's what causes these crazy patterns. And because of that, this, if I were to go back to this Mackey glass, and you can start seeing kind of hints of those, that period doubling, these oscillations of these little bumps, these patterns will never repeat. It is not a stable oscillation. You now can get basically, I mean, they look similar to each other, but every hill here is slightly different than the hill that came before it. Like you can see this red point right here is very different than the red point here and is not quite the same as this point here. So you end up getting this system behavior that at a global scale, if you were to sort of, you know, go far out, it looks like it's staying roughly around here, which it is. But at a local scale, it's like every little bounce is different than every other bounce. And that's chaos right there. It looks random, but it's totally deterministic. It's just the delays and the nonlinearities of the system make it very, very sensitive. It's like an initial condition sets its trajectory for the rest of its life, and that trajectory never repeats. And if you don't know the initial condition, you don't really know what trajectory you're on. And every trajectory looks very different than every other trajectory. And we'll find a better way to visualize that in just the next example here. Yeah. That's right, that's right. So this part, once the initial condition's set, the rest of it deterministic. If you happen to know precisely where the system is, you can predict where it will be. That's the reason why a computer program, you go into 212, you draw this thing, you load it up with this equation, you hit play, and you will get this out because the computer can say, given the initial condition you gave me, I can predict the rest of it. But, and they talked about this in your book, that just knowing, like simply saying, oh, we're going to know the initial conditions well enough that we should be able to predict how the universe is going to unroll itself is not enough, because we have systems like this. This simple system, one state variable, one endogenous variable, that's another way, another term for endogenous variable, state variable. With a single state variable, an expression that's kind of ugly, but not that bad in some delay, then if you don't know your initial conditions perfectly, then there you go. Anybody seen Jurassic Park? Old movie now. So Jeff Goldblum, he's flirting with Ellie, has her hold out her hand. Does anybody remember the scene? Does anybody know what I'm talking about? Jeff Goldblum. So at one point, the scientist is meeting the mathematician for the first time, and Goldblum says something flip about, oh, it's chaos. There's no way they know how this island's going to unroll. And she said, oh, what do you mean? And he goes, well, it's like this. And he has her put out her hand. And then he drops a droplet of water on her hand, and it flows off towards her thumb. And then he does the same thing. He drops the droplet of water roughly on exactly the same spot on her hand, and it rolls out towards her pinky. And he does it again, and it keeps going to different spots. He said, even though you think you know where you started, these very, very tiny changes in where it lands on the top of your hand determine the whole future of this whole thing. So there are some systems where an approximation, getting it almost right, is not going to be enough. This is why we think we can't predict weather more than a couple of days, because the systems that best model what goes on in the sky have these features. They are chaotic, and like the system I'm about to show you. And because of that, even though you can sample everything about the atmosphere today, you're not able to predict the atmosphere much farther than a few days in the future. That's your few day prediction, because after this, the chaos kicks in, And you find out that your 20-day predictions are wildly different if you make a small change today. That's the butterfly effect. Anybody who tells you the butterfly effect is about a butterfly flapping its wings and causing a hurricane on the other hemisphere does not understand what they're talking about. The butterfly effect is not about a flap causing something. The butterfly effect says in a world where the butterfly's wings are up, you get one weather pattern. In a different world where the butterfly's wings are down, you get a different weather pattern. And if you're trying to figure out which world you're in, to figure out, you know, what to wear next week, you have to know whether the wings are up or down. That's chaos, an extreme sensitivity to tiny differences in dimensional conditions. And that's the butterfly effect. So questions about that? Okay, so with that, I do want to show you one other system here, because it turns out that delay isn't the only thing that can cause chaos. The other thing that can cause chaos is having 3 or more state variables, 3 or more endogenous variables. So not all systems with delays or 3 or more variables will be chaotic, but you can't have chaos without one of these two things, either nonlinear feedback and delay or nonlinear feedback and 3 or more endogenous variables. So if you have 3+ endogenous variables, which by the way, we also call state variables in dynamical systems, plus nonlinear feedback, then you also can get chaos. And I mentioned this kind of before, is if we try to think about that ball and basin model, where we've got height, and we've got maybe some variable x as an endogenous variable, some variable y. So this is, I'm just going to say an endogenous variable, an endogenous variable. Well, if our z-axis is taken up by height, then we have to say, well, where's our third endogenous variable going to go? If it matters, if you can't know what x is going to do without knowing what y and z are going to do, how do I represent z? Well, you could say, well, what if I make a ball here and I make the color is equal to my z variable? So, you know, it could be, you know, red, blue, etc. And each color represents a different value of z. Well, that's a fine way to visualize it, but it's what happens though is it's like your basin. It might be that you're going to have a red basin. Look, when the ball is red, it's going to roll around on a basin that looks kind of like this. There's this like saddle point. But if the ball flips to a different color, like this blue color, then maybe the basin actually rolls around on a very different shape that looks, you know, something like this. And if it was an even different color, maybe it's the shape is completely different from that. So it's really hard to use these ball and basin models when you have 3 or more endogenous variables, because you have to imagine the shape of the basin changing with the other variable. It's almost like the endogenous variable, the fast variable, is acting like an exogenous variable. So it's pretty much all of our intuition when you have 3 or more of these variables just doesn't work. Ball and basin models just don't work. And so if you add in nonlinear feedback to having these 3 variables, then it's just really hard to see what's going to happen. And so an example of this is this Lorenz system. And Lorenz was a meteorologist. So this is a model of atmospheric convection. And in order for him to get patterns that looked like the patterns we see in real atmospheric convection, he built this this model here. And I guess I could write it down, but maybe it's easier for me to just copy the system over. because again, it's not important for you to know the Lorenz system. I will not ask you to recite the Lorenz system or anything like that. It's not that type of class. But this is the Lorenz system, a simplified mathematical model of atmospheric convection. And you can think of this as the change in endogenous variable X. I don't know what X, Y, and Z are off the top of my head. Like, this could be like pressure, temperature, something could be three sort of physical variables, but they're all sort of written this way. So the change in X has to do with both change in Y and X. So this, by the way, is linear. But down here, this is nonlinear. And this right here is nonlinear, even though this over here is linear. And this over here is linear. So we see here that we have nonlinearity, nonlinear feedback, and 3+ endogenous variables. And it's not that complex of a system. This is what it would look like in kind of SOS 212 language. So so this is like the SOS 212 version. So after you take 212, you could have somebody give you something that looks like this, and you could go into a computer and draw this, and it would then, you could hit play, and you could see the behavior over time of this system. So what you'll learn how to do in 212. So, and this isn't that complex of a diagram. So you do that, and what do you get out of it? Well, let's grab here is an example that I simulated using Vinsim. And we've got multiple initial conditions that are kind of close together here. So we've got three systems. So this is X, Y, and Z. I'm plotting all three endogenous variables in different plots here. So I've got an initial condition, say, of X, of Y, and of Z. And then it moves, all three of those move forward together. And then I have another case where I have a different X, a different Y, and a different Z, and all three of those move forward. And then another one, a different X, a different Y, a different Z, and all three of those move forward in their behavior over time. And they're colored differently. So I've got the one set, the other set, and the other set down here, blue, red, and green. And so that's how they're connected across here. And just like in the Mackey glass system, they start out at all three initial conditions that which were close together, start out with roughly the same pattern. But then they hit some point and they just start diverging. And you get a very different pattern. Like if you look here, the colors are like super diverged. So you get a very, very different pattern from the three initial conditions, even though the initial conditions are extremely close together. And this again is why we think we can't predict the weather past a certain amount of time, because the weather is described by chaotic models. Those chaotic models have limited predictability, especially as if your initial conditions are way off. So if you don't know your initial conditions just right, then you'll get a very different trajectory that comes out of here. Now, one of the cool things we can do with the Lorenz attractor, so this is, again, so this is chaos. So I just emphasize this, chaos. So extreme sensitivity to initial conditions. And this is a strange attractor. So it is globally stable, but locally unstable. But now that I've got more than one endogenous variable, I can do that parametric plot thing where I can plot them together and just see what I get out. And so if I do that, Instead of plotting the behavior over time, I plot a parametric plot. And so now I've plotted X and Y together so that every point corresponds to, this is a trajectory. So this is one trajectory here. And so for that trajectory, this is a current value at one time. It's got this X and this Y. And then a little bit later, it'll have this X and this Y. A little bit later, this X. And so it will evolve along this curve like this. Now, if I use a different initial condition that on the previous slide gave me a very different looking behavior over time, the parametric plot, plotting X versus Y, gives me roughly the same picture. So even though in time, it's the X trajectories and the Y trajectories look extremely different from one initial condition to another, the relationships between X and Y are the same across all of these initial conditions. And so one of the ways we look for chaos in nature is plotting the endogenous variables against each other. Because if it is truly random, then you plot them one against the other and there won't be any relationship. It'll just be like a scatter shot across the graph here. But if you have sort of a weird thing going on in like, atmospheric pressure and another weird thing going on in density or something like that, and you plot them together. So this pressure was found at this density, this pressure was found at this density, and so on. When you get something like this, that is structure. That is showing that it's deterministic underneath it all. It's just a weird attractor, a strange attractor. And so this is picturing that strange attractor. Now, remember I said there were 3 variables. And so I can actually show you an animation of all 3 of these. I probably already have it loaded up and it's linked on the Canvas page. So this is going to rotate in a second. This is the Lorenz attractor in 3 dimensions. So in a second, it'll rotate so that now we're looking at Y and Z together. And we're watching one trajectory evolve. That's what the little red dot is. And then it'll rotate. And this looks more like what I showed you, X versus Y, and it'll keep rotating. So it is a weird 3-dimensional shape in the endogenous space here, in the X, Y, Z variables, that we can't describe as an oscillation because it doesn't have any periodicity. It doesn't repeat, but it stays on the shape. It's this weird shape that if you were to start the initial conditions out here, it would be attracted to it, and then it just rotates around it, and it never repeats the same path. There's enough space in the continuum for it to be able to traverse this shape and never cross its own path. And that's a crazy thing about it, and that's a strange attractor. The questions about that right there is chaos. That is true chaos, yeah. Well, a Mobius strip might be, yeah, so a Mobius strip is an interesting example. So that's like, N.C. Escher drew the Mobius strip, and that's kind of a strip that kind of comes on itself. And that's an interesting mathematical object that is certainly, I would say, related to the types of shapes that you can get out of these things. A Mobius strip isn't necessarily a strange attractor because you can start on a Mobius strip, and like if you walk down the middle of the Mobius strip, you would kind of walk twice around the Mobius strip, but you eventually would come back to where you started. So, and even if you kind of like went off at an angle, it still has much more periodic motion than this, which you never end up where you started. You just keep walking forever. Yeah. Well, yeah, it's predictable. If you knew the initial conditions perfectly, it's predictable, but you never will. So that's the danger in chaotic systems, is that, and so that's what I think, Mitchell talked about in the text, is that in the history of dynamical systems, when Newton came up with calculus and we realized we could describe things that change over time with these formulas. They're ugly formulas, but you can write them on a page. They're compact. We have the tools that we can then evolve them forward and predict things over time. And that's when people like Laplace came around and came up with the so-called Laplace's demon. He said, if we knew the position of every molecule, in the universe, then we should be able to know what's going to happen for all future. That it's predetermined. That was Laplace's demon. If there's a demon that knows everything at this instant in time, they know everything at all instants in time. And so people thought that was it. Determinism does it. As long as we measure things finely enough, we'll be able to make predictions forever, thanks to Newton. And then this stuff like this came up. Like people like Lorenz and Poincaré started to notice that even like Newton solved gravitational problems for two bodies, like the moon and the earth. But when you go to three bodies, three endogenous variables, you get chaos. And that's what Poincaré realized, is that you can't use Newton's equations to simply solve the three body problem, because if you're slightly off about where one of the planets is, the trajectory looks totally different. So, and there's no way we're ever going to know the precise position of every planet. So, so basically, that threw predictability out the window, even though in theory, the fundamental dynamics are deterministic. The kinematics, really, the shapes that things draw over time, there's no way you're going to be able to figure those out, because there's no way you're going to be able to measure the initial conditions finely enough. Yeah. That's a great question. So like, I mean, I would say that, yes, so there is, this is outside of the scope of this class, but there's something called a Lyapunov exponent, which is basically a measure of how quickly initial condition differences diverge. And in chaotic systems, in normal systems, they don't diverge, they collapse. But in chaotic systems, they grow. And we can actually measure, for some systems, they have a higher exponent than others. So they very quickly become very different. And so, and you can kind of see that in the Mackey glass system, I felt like it actually diverged more quickly than this system. But I haven't actually measured the Lyapunov exponent of these two, but you could. And so in general, that's the case, but you really don't get much time before things blow up and become very different from each other. Yeah. Yeah. That's right. That's a great question. It turns out that if these lines cross, that's equivalent to returning to the same point. And so, so yeah, I mean that these lines will never cross. And that's the reason why chaos can't exist in 2 dimensions without delay. Because if you try to draw this shape in 2 dimensions, you'll force yourself to cross lines. But in 3 dimensions, there's always a way around to keep yourself from crossing. Any other questions? Yeah, well, this is an animated GIF, so it is because the GIF recycles. But if this were to go on forever, then the ball would always come close to where it was before, but it would never go to the same spot. Yeah. Any other questions? All right. So with that, so any reflections from the chapter? So I just wanted to provide, and the chapter was basically a bunch of complex systems. We've talked about those before, and this history of where chaos emerged from. Did anybody have any thoughts, or was it a good chapter? Was it a bad chapter? Any questions? Hopefully this provides some context. Just to make sure there's yeah, we covered basically all the big things. The only other thing I think I might mention is that she mentioned something in the chapter that she doesn't consider a hurricane or a turbulent water flow to be adaptive, but they are complex. And I just want you to sort of think about that distinction. A hurricane, it's not like you can throw something into a hurricane that destabilizes it and it will figure out a new way to operate. A hurricane is either kind of churning or not. And that's why we would think of it as maybe not adaptive, but it is complex because we can't really associate, cogs of the machine that is the hurricane. So I thought that was a nice distinction too. Yeah. Well, I would say, yeah, hurricane is sort of driven by its force. And yeah, it doesn't, if you had a force that was strong enough to disrupt a hurricane, you would just extinguish the hurricane. It wouldn't turn. Yeah, well, then that's like a new system. So like a system of hurricanes might be a complex adaptive system, but a hurricane itself is just a complex system. All right, well, that's chaos and we're caught up. So I'm excited about that. I'm going to go back to the attendance slide here to get you out of here on time. Question here is, how many endogenous, if you have delay in your system, what is the minimum number of endogenous variables you need to get chaos? So I'm giving you delay for free. How many endogenous variables do you need to possibly get chaos if you have delay? And that's all I've got for you. So don't forget Muddiest Point this weekend. There's a reading on Tuesday, and there's a couple assignments for C and D that you have the opportunity to do. I think that's about it. Thanks. You too.